You know, when we picture an oil well, we usually think the story's over once the drill bit stops spinning. But honestly, that's where some of the most fascinating engineering really kicks into gear. So let's talk about what happens after the hole is drilled, a whole process called well completion. Okay, so you did it. You've drilled thousands of feet underground and hit your target. You have a wellbore. Now what? The huge question for every engineer on that job is, how are we going to get the oil and gas to actually flow out of that rock and into our well and do it efficiently? On the surface, the goal couldn't be simpler. Get as much out as possible. But the thing is, the rock formations down there are almost never that cooperative. Seriously, every single one is a totally unique geological puzzle that has to be solved before a single drop of oil is ever going to see the light of day. To really get why the solutions are so clever, we first have to wrap our heads around the number one enemy that engineers are battling deep, deep underground. And that number one enemy has a really simple name: skin. The best way to think about it is like a massive 5-lane traffic jam that suddenly squeezes down to 1 lane right at the exit ramp. You see, the act of drilling itself can actually damage the rock or clog up all the tiny little pores right around the well. This creates a bottleneck, a zone of really low flow, that's the skin, and it can literally choke production. So you could say the entire point of well completion is to figure out how to get around or just get rid of this skin.
So, what's the easiest way to deal with this skin problem? Well, in a perfect world, the geology pretty much does all the heavy lifting for you. This best-case scenario is what's known as a natural completion.
Now, this approach only works if you've basically hit the geological jackpot. We're talking about a near-perfect reservoir. You've got stable sandstone that's just naturally super permeable, meaning fluid can flow through it like water through a sponge. The magic number you're looking for here is a permeability over 10 millidarcies. If you've got that and the skin damage from drilling is minimal, you are in fantastic shape. In this kind of dream scenario, the fix is pretty straightforward. You just perforate. Engineers use these powerful explosive charges to punch a bunch of holes through the well's steel casing and the cement, creating little tunnels that lead directly into the good rock. And here's the key insight. It's not about how big the holes are. What really matters is how deep they go and how many of them you can make. It's all about creating a ton of deep pathways that just bypass any of that minor skin damage. So yeah, that's plan A, when everything goes just right. But like we said, geology is rarely that nice. So what do you do when the rock is too tight, not very permeable, and that traffic jam, that skin damage, is just way too bad to ignore? This is where engineers have to get creative. They have to go beyond just poking holes and actively stimulate the reservoir to force it to produce. And this whole family of techniques is called stimulated completions. In this stimulation toolkit, engineers have 3 main power tools they can turn to: hydraulic fracturing, acidizing, and a really intense method called extreme overbalance perforating. And each one is designed to solve a very, very specific kind of problem down there. All right, so let's open up this toolkit. Let's take a closer look at how each of these tools actually works and, maybe more importantly, figure out the specific situations where you'd pick one over the others. First up is the one you've almost definitely heard of: hydraulic fracturing. This is the go-to method when you're dealing with rock that has extremely low permeability, what people call tight formations. Here, the goal isn't to clear out old pathways. No, the goal is to create a brand new, man-made superhighway for the oil and gas to travel through. The whole process is actually a pretty precise multi-step dance. After prepping the well, engineers use high-pressure fluid to start a crack in the rock. Then, they push that fracture deeper and deeper into the formation. Now, here comes the most critical step. They inject something called a proppant. It's usually just sand, and that props the crack open so it can't close back up when the pressure is turned off. After that, they just clean out the well, and you're ready to start production. Okay, now for a totally different strategy: acidizing. So if hydraulic fracturing is like building a whole new highway, you can think of acidizing as calling in the ultimate road repair crew. Its main job is to fix existing damage by dissolving all the gunk, the debris and minerals that are clogging up the rock's natural pores right near the well. And there are 2 main ways to use acid. The first is matrix acidizing. Here you use low pressure. You're just letting the acid kind of seep into the rock to dissolve any plugs in the existing pathways.
But with acid fracturing, you use high pressure to actually crack the rock first. Then the acid goes in and etches the sides of that new crack. So when the pressure comes off, the crack closes, but those rough, etched surfaces don't seal up perfectly, which leaves a brand new path for oil and gas to flow. One huge plus for acid fracturing is you don't need to use proppant, which makes the whole operation a lot simpler. But there's a trade-off. You lose some control. Sometimes the acid dissolves the rock unevenly and creates these really inefficient little channels that engineers call wormholes, instead of one nice, uniform fracture. And finally, we've got the most, let's say, dramatic option on the list: extreme overbalance perforating, or EOP. This technique is brilliant because it combines the perforation and the stimulation into one single, incredibly powerful blast. The whole idea is to hit the rock formation with a massive shockwave of energy at the exact same instant the perforations are being created. Here's how it works, and it happens in a flash. First, engineers use nitrogen gas to build up a crazy amount of pressure inside the well, way more than what's needed to fracture the rock. Then, while it's under all that pressure, they fire the perforating guns. This sudden release creates a huge shockwave that blasts stimulation fluid deep into those brand new tunnels before the rock around them even has a chance to react. So we've just walked through 3 very different ways to stimulate a well. And all of this brings us to what is maybe the most important rule in all of well completion engineering. And that rule is really simple. There is no single best method. There's no silver bullet. You don't just pick the most powerful tool in the box. The choice to use hydraulic fracturing or acidizing or EOP comes down entirely to a super careful diagnosis of the specific geological puzzle you're trying to crack. Let's just break it down one last time to make it crystal clear. If your main problem is that the rock itself just doesn't flow well, low permeability, you turn to hydraulic fracturing to build new highways. If the problem is just some localized damage, clogged pores right around the well, then acidizing is your go-to repair tool. And if you need a really powerful, targeted kick right at the moment of perforation, that is a job for EOP. See, in the end, it doesn't matter if it's a simple perforation in a perfect reservoir or a massive, complex, multi-stage frac job. Every single decision an engineer makes comes right back to solving that one core problem we started with: beating the skin and clearing a path for that energy to flow. The techniques we've just talked about are unbelievably powerful and precise. They represent decades and decades of innovation. And as we try to figure out our complex energy future, it really does raise a pretty big question. Is this kind of sophisticated engineering part of the problem, or is it an absolutely essential part of the solution?